Okay, so let's do one more related rates problem before we go on to the next section. So let's say the edges of a cube are expanding at a rate, let's say 5 centimeters per second. Find the rate, the volume of the cube, the rate that the volume of the cube is increasing when each edge measures, well, let's make it 30 centimeters. Okay, let's go through our steps. Step 1, draw a picture if it's possible. In this case, it's certainly possible. Step 1, picture. Step 2, let's define some variables. We need a variable for the length of the edge of a cube. How about just L for length? The length, width, and the height of a cube are all equal. So that's one of the variables we need to define, because that's one of the variables mentioned in the problem. The length of each edge. So look through the problem and decide what the other variable is. So if you're looking through this and you spot the word volume, and you want to relate the rate at which the volume is changing to the rate at which the edges are changing, then our other variable has to be volume. Probably the easiest way to do this is just to write V equals volume. So important to define your variables, not only because you'll lose points if you don't, which is sort of an artificial reason, but your reader will have no idea what you're talking about unless you do define your variables. So it's sort of a good time to talk about the point of writing up a solution. I think in high school, oftentimes what you see is sort of rough work, then conclusion, or solution or whatever. But what you're trying to do here is explain to other people what your thought process is. It's a lot like writing an essay. And so keep an audience in mind. You don't have to assume your audience is made up of idiots. You can assume your audience is made up of intelligent people. Just assume they know a little bit less about what you're talking about than you do. So make sure that you define everything carefully so they can understand your thought process, they can understand your conclusion, they understand that why what you're saying is true. Now, the other reason we want to define our variables is everything else in the problem depends on that. So if you can get your variables defined, you have a really good shot of completing the problem. So step 1 and step 2, we have our picture, we have our variables defined. Step 3 is to write an equation which connects our variables. In a cube, what relationship connects volume and the length of a side? So you know in a cube, the volume of a cube is the length times the width times the height. In this case, they're all L. So the volume is going to be L times L times L, or L cubed. V equals L cubed. That connects our two variables. The next step in a related rates problem, we've already finished section, part 3. The next section in a related rates problem is to take the derivative of both sides always with respect to time. Take the derivative of both sides always with respect to time. And so if we take the derivative of v with respect to t, that's just dv dt. I suppose you could write that as v prime, and that would be totally fine. dv dt emphasizes that the variable you're taking the derivative with respect to is time, and that can be helpful. Derivative of L cubed, we're going to need the chain rule for that. 3 comes down. We write L exactly as it is. 3 becomes a 2. And then at the very end, we multiply by the derivative of L, which is dl dt. So we started off with a formula which connected our two variables. We took the derivative of both sides and then ended up with a formula that relates the rates, hence the word related rates. Step 5, go back and write down what you know and what you don't know. So we happen to know that we want the length to be 30 centimeters. And dl dt, the rate at which the length is changing, make sure that this and this are actually meaningful in your head. dl dt, the rate at which the length is changing. dv dt, the rate at which the volume is changing. Those two things have to speak to you. So dl dt, 5 centimeters per second. And dv dt is what we're looking for. You don't have to write dv dt equals question mark. I tend to do it because it reminds me what it is I'm looking for. So let's go ahead and plug all the stuff we know into the problem here and solve for what we don't know. Again, I'm not going to make you carry units all the way through as long as they're in your answer, but I do want to include them here for my own purpose, just to show you how nice that the units all work out. So dv dt is equal to 3 times L squared times dl dt so what do we have? 900, what, 2,700 times 5, what would that be? So 13500. Somebody better check my arithmetic.
That's right.
That's okay? Okay, good. And then centimeters times centimeters times centimeters is centimeters cubed divided by seconds. See how nice the units work out? So if we had 2 centimeters here, a third centimeter here per second. So this is a rate at which volume, centimeters cubed is the rate of volume per second. So that's the rate at which a volume is changing, which is exactly what we're hoping for. And let's write a concluding statement. So the volume is increasing at a rate of 13,500 centimeters cubed per second when the edge length is 30 centimeters. So one thing that may or may not be clear to you is that even though the edges are increasing at a constant rate, the volume's not. You can see there's a space for length here. So the bigger the length gets, the faster the volume's increasing. I don't know if that's intuitive to you or not, but if I still said 5 centimeters, but I asked you to do it at 60 centimeters rather than 30 centimeters, the volume would be increasing what 4 times as fast at that point. And you have a homework problem where you can see that this phenomenon taking place. Now, one other thing I wanted to mention, what was it? Oh, yeah, way back here. When you're drawing your picture, resist the urge to put 30 centimeters here and here and here. You really don't want to do that because then you have no variables to work with. So if you're going through the problem, you drew your picture, you put some numbers on it, and all of a sudden you're not sure what your formula should be that connects two variables, it's almost certainly because you put numbers for something that should be changing. You don't ever put numbers if a value is changing. So this 30 centimeters, this length is only 30 centimeters for an instant. It's actually changing. So we definitely need a variable for that. So I would say most of the time when people get in trouble with a related rates problem, it's near the beginning. If you can get, say, this far or especially that far, you're probably in pretty good shape for the rest of the problem. I mean, you might make an arithmetic mistake, you might make an algebraic mistake, but the main structure of the problem is set by that point. So usually when things sort of totally fall apart, they fall apart back here, or here. Okay, so that's it for related rates, and that's it for chapter 2. Let's move on to chapter 3.
Can you reread your explanation? Explained.
That word, in case it's blurry, is extrema, E-X-T-R-E-M-A. Extrema on an interval. So I'm going to start off with the definition of what's called a global or an absolute extremum. So let I be an interval, an open or closed interval containing the value C. We say that the function f defined on I has an absolute or sometimes instead of the word absolute, we use global maximum at x equals c if f of c is at least as big as f of x for all x in the interval. And likewise, we say F has a absolute or global minimum on I if F of C, sorry, global minimum on I at x equals C if F of C is less than or equal to F of X for all. I'm going to use a symbol for all this time. I introduced that symbol at the beginning of the semester, upside down A for all X and I. So if you don't like that symbol, just write it out in words, but you should recognize that symbol. So absolute maximum, absolute minimum, or global maximum, global minimum, they mean the same thing. So don't let this turn into some sort of linguistic nonsense. All we're looking for is, all we're saying is we have, the function has its highest point at C. It's never higher than it is at x equals C in the first case, and it's never lower than it is at x equals C in the second case. So let's just draw ourselves a little picture. Let's say here's our interval here to here. Let's say this is x equals A, and let's say this is x equals B, and let's draw ourselves a little picture. No, that's not clear enough. Drawing some vertical lines first. There we go. That's better. And let's just mark this point C. So this is a graph y equals f of x. Let me dot in some horizontal lines too. At least that one. So in this picture, so where I is the interval AB, at what x value does f have an absolute maximum? Where is f the highest?
A.
Yeah, at x equals A. So f has an absolute maximum in our picture here. At x equals A. So you can see this y value right here that corresponds to x equals A is f of A. And the y value, f of A, is at least as big as f of x. It's at least as big as f of x for any other x value in this interval I. No matter what other x value is, the y value is lower than it is at f equals A. Let's see. And f has an absolute minimum on I at what x value? Where's the smallest? What x value leads to the smallest y value? Really only 3 to choose from.
C.
2 now.
C.
Yeah, C. You can see that f of c, the y value that corresponds to the x value c, is lower than the y values for any other point on the curve. So I'm going to erase this, but you're going to need your notes for this to answer the questions that are coming up. So keep an eye on those. Can a function f defined on an interval have an absolute maximum at 2 different x values? So look carefully at the definition of absolute maximum. Can you have an absolute maximum occurring at 2 different x values? How about vertical head motion for yes, horizontal head motion for no, or thumbs up, thumbs down? So I see a thumbs up for yes, another thumbs up for yes. Yeah, you're absolutely right. So we can certainly have an absolute maximum at more than one x value as long as those 2 x values have the same y value. So for instance, let's say here's my interval from here to here. It doesn't have to be a closed interval, it could be an open interval. So from there to there is my interval. Let's say I have something that looks like this. Right there. As long as I hit the same height, my max, I hit that same maximum height twice, I can certainly have an absolute maximum at more than one x value. So that's A and that's B. Let's call this C and D. So we have an absolute maximum on I at x equals C and x equals D. And you can see that f of C and f of D are the same, and they're bigger than f of x for any other x value between A and B. So here's f of C, it's also f of D. They're the same height. So yeah, absolutely, we can hit an absolute maximum at 2 different x values. So an extremum is just a maximum or a minimum. And in terms of the language, the singular for maximum is just maximum. The plural is maxima. And for minimum, it's minima. And for extremum, which is just a word that means maximum or a minimum, it's extrema. Now you understand the title of the section. So now a harder question. Can a function f defined on an interval of an interval of your choice fail to have a maximum? Can it not have an absolute maximum? Look over here since that's where you are on my screen. So could there be no highest place on the curve? That's basically what I'm asking on an interval. So Robert, you say no. Valentina, you say yes. And Nathaniel, you also say yes. Okay, that's interesting. So we have some disagreement here, which is great. You're all thinking this through. As it turns out, the answer, did somebody want to tell? So the answer is yes. Does somebody want to give me an example that they have in their head? If not, I can give you a few. So the answer is yes, it can happen. Let me give you one example. So let's start off with my interval being, let's say, negative infinity to infinity. Perfectly nice interval. And let's let f of x equal x. So you know what the curve y equals x looks like. It's just a straight line going uphill at 45 degrees, crossing at the origin. There's no highest place on that curve. No matter where you're standing, I can move to the right and stand higher. Now you might be saying to yourself, well, that's kind of cheating. You used an infinite interval. So let's see if we can do this with an interval that's not infinite. Let me give you a different interval. I'm going to use the same function. How about we use the interval -1 to 1? Oh, by the way, this first one has no maximum and no minimum. There's no absolute maximum, no absolute minimum. We often just write maximum max and minimum min. I'm totally okay with that. So let's use the interval, open interval -1 to 1, and I'll use the same function. F of x equals x. Let's sketch this. Well, all we have is the part of y equals x between -1 and 1, not including x equals 1 and not including x equals -1. So we still have this line going uphill at 45 degrees, but it only goes as far as 1 and then open circle because it doesn't include the point at x equals 1, and open circle here because it doesn't include the point at x equals -1. There is no highest place on this curve. I mean, I can stand right here. I don't know if you ever played like King of the Hill with your sibling. You could stand right there at, say, x equals 0.9, and you're at height 0.9. But then your, silly little brother can run a little bit higher on the curve. They can go up to 0.99, and they're at height 0.99. This curve just has the y coordinate, same as the x coordinate. And then you can go, well, I'll go a little bit higher. I'll get a little bit closer to 1, and I'll be even higher. I'll be higher on the curve. But you can't stand at 1 because it's not part of the interval. So there's no highest place on this curve. There's also no lowest place on this curve. So in these two examples that I have over here, the problem seems to be with the interval so far. Here I used an infinite interval. Here I used one that didn't include the endpoints. Is everybody okay with what we're doing so far, that in both the first and the second example, there's no highest place on the curve and there's no lowest place on the curve, and the problem seems to be with the interval? Can you give me like a thumbs up if that's making sense? Okay. Okay. Any questions so far? Let's see if we can do one with a closed interval, a closed and bounded interval. You actually can. It might be a little bit harder to imagine, though if anybody has some ideas you might want to toss out, feel free to. I want the function to be defined everywhere on the interval. Let me give you another example. This time I'll take I to be, let's say, the interval from 0 to 1. Closed interval from 0 to 1. And let's say, here's a graph of f. I'm just going to draw it. Put that lower. So let's say here is x equals 0. Here's x equals 1. So I want the interval from here to here. So I'm going to start off at a height 1/2. I'm going to, let's go to x equals 1/2. I'm just going to dot some lines in here so I can see what I'm doing. Making my own graph paper. So from here, oops, closed interval, so I have to have a closed circle. From here, all the way to here, and then I'm going to have an open circle. Then I'm going to put a closed circle right here. And then an open circle here, closed circle here. There's a function. If you want like an algebraic formula for that function, no problem. F of x equals, say, x plus 1/2 if x is between 0 and 1/2. I just took the straight line, shifted it up 1/2 unit, straight line, slope 1, shifted up 1/2 unit. And at x equals 1/2, I'm at 1/2. And if I'm between 1/2 and 1, it's x minus 1/2. So that's just that. I don't need this. This picture's perfectly nice. And hopefully you can see that there's no highest place on this curve. There's no place I can stand that's higher than anywhere else. I mean, there's some high places over here, but there's no highest one. I can get closer and closer to x equals 1/2 and get higher and higher. But if I stand at x equals 1/2, I'm not up here, I'm down here. Likewise, there's no lowest place on this curve. There's some low y values over here, just a little bit bigger than a half, and I can get closer and closer to y equals 0, but I can't stand at y equals 0, because if I stand at x equals 1/2, I'm up here. So there's no highest place and lowest place on the curve. So I've given you 3 examples of functions and intervals, the functions defined everywhere on the interval, where in each case, the function had no maximum and no minimum. And again, in my first 2 examples, I think we'd probably agree that the problem was with the interval. And with the third example, I think we'd agree that the interval is about as nice as the interval could be, this nice closed interval, but the problem was with the function. So I'm going to ask you a question that's going to result in a theorem, our second big theorem of the course. The first one you'll recall was the intermediate value theorem. So what would we have to assume based on our experience now? So what would we have to assume about an interval I and a function f defined on that interval to guarantee that f has both an absolute maximum and an absolute minimum on I. So it has both a place that's at least as high as everywhere else and a place that's at least as low as everywhere else. The answer to this question, hopefully you're forming some hypotheses in your mind right now, but the answer to this question is called the extreme value theorem. And just like we abbreviated the intermediate value theorem, IVT, we abbreviate the extreme value theorem, EVT. We have one more theorem coming with a similar name, that's the MVT. A few days before we get there. So the extreme value theorem. So we know we need something to do with the interval and something to do with the function. And again, you may have a correct hypothesis in your head as to what those 2 assumptions need to be. So if, first, I is a closed interval, let's say, of that form. And secondly, f, what property did I sort of not have in that third example that I had over here and have since erased? F is continuous, no breaks on I. Then f has both a maximum, has both an absolute maximum and an absolute minimum on I. So if I is a closed interval and f is continuous on I, f has both an absolute maximum and minimum on I, guaranteed. If one of the hypotheses is false, you might still have the conclusion true, or both the hypotheses are false, you might still have the conclusion true, but you don't know, not from the given information. But if both of these hypotheses are true, the conclusion is true for sure. Let's take a look at an example. Let's say I is the interval 0 to 2, and let's say f of x equals the constant function 1. Let's just sketch a little picture here. So I'm only concerned about what's going on between x equals 0 and x equals 2. And y equals 1 is just the horizontal line at height 1. I only want the part between 0 and 2, including my 0 and including my 2. So put little closed circles at the end. Now you can see that this certainly is a closed interval. I have a bracket here, a bracket here. And this is certainly a continuous function. We know this thing has an absolute maximum and an absolute minimum on the interval. You might be going, wait, where is it? But yes, I thought you had your hand up. So you actually have your absolute maximum and your absolute minimum at every single value of x. If you take a look back at the definition of absolute maximum, you'll see that to be an absolute maximum, you have to be at least as high as every other point. Well, at x equals 1/2, I'm at least as high as at every other point. At x equals 2/3, I'm at least as high as at every other point. At x equals 0, I am at least as high as every other point. And likewise, every point on this horizontal line is at least as low as every other point. So every point on this curve is both an absolute maximum and an absolute minimum. Okay. So hopefully everybody has the extreme value theorem in this example copied down. I guess one of the nice things about the way we're doing things now is you can always go back and look at the video. So another definition, instead of talking about absolute or global maxes and mins, we can talk about something called relative or local maxes or mins. If there exists an open interval I containing x equals c, upon which F has an absolute maximum. Oops, something went wrong there. Absolute maximum on I at C. We say F has a relative or local maximum at X equals C. And similarly, we can define a relative minimum. Just replace the word maximum wherever you see the word, with minimum, wherever you see the word maximum. So in other words, the relative maximum is just the highest place in its own vicinity. So we have a relative maximum at X equals A. That's the highest, that's like the top of a hill. It's the highest place in its own little vicinity. And even though at X equals C, we're lower than we are at X equals A, we have another relative maximum at X equals C. And we have a relative maximum at X equals E. So we have relative or local I think makes a lot of sense here, relative maxima at X equals A, X equals C, X equals E. And we have relative minima at X equals B and X equals D. They're the lowest places in their vicinity. So you can have an absolute maximum only at a single height, but you can have relative maxima at different heights. They just have to be the highest places in their own little vicinity. Is that making sense? Well, I seem to have used up the time today, so I will see. Awesome. So I will see you all on Wednesday.
Thank you. Have a good day.
You too.